Medical chemistry in organic synthesis. My name is Karen Muirhead, and I'm Senior Executive Editor for Science of Synthesis. And today we have three great talks, and our chairs today are Louis Fensterbank and Cyril Olivier, with a brief overview of some of the key points to help facilitate today's session. So firstly, the Cheminar is being recorded, and that's so that others who haven't been able to make it to the live event can watch the session afterwards. So to avoid any interruptions during the presentation, please to use the question and answer window within Zoom to do this. We'll try and answer as many questions as we possibly can at the end of each presentation. So please social media channels by tagging us Thieme Chemistry links on LinkedIn or on X. And if you're interested in hearing more about our Cheminar series or subscribing to our Thieme Chemistry newsletter, you can do so using the links on the screen here too. For those who aren't aware, Thieme is a German company with an international presence and over 130 years of experience publishing science. Chemists acquire knowledge and about organic chemistry, as well as helping to devise efficient synthetic strategies. You're probably familiar with our scope to involve areas such as sustainability and green chemistry. We also have a suite of biomedical journals, which are not shown on this slide. Today's Cheminar is presented by Science of Synthesis, which is our text and structure searchable resource for methods in synthetic organic chemistry, and under the guidance of Scott Sieberth. And after a lecturer position at the Pierre and Marie Curie University, UPMC, he was appointed as a CNRS charge de recherche in max molecular radical or organometallic processes and their applications to the synthesis of substrates with relevant properties. He's co-authored more than 250 publications and received several awards, notably the Silver Medal of the CNRS in 2017. Collège de France, and holds the chair Activations in Molecular Chemistry. Our second chair today, Cyril Olivier, obtained his PhD in collaboration with Max Malacria. He was awarded a Swiss National Foundation Fellowship to work with Philip Magnus at the University of Texas at Austin, and in 2002 was appointed Charge de Recherche CNRS at Aix-Marseille University, and then he moved in 2007 to the UPMC, Sorbonne University, where he's now CNRS Research Director at the Paris Institute of Molecular Chemistry. And he develops new research in synthetic radical chemistry and organometallic catalysis, including photocatalytic. With that, I'd like to hand over to Louis and Cyril and ask them to introduce the first of our great speakers today. Thank you.
Thank you, Karen. I will start. Actually, Cyril will follow for the next presentation. So today,
a little bit an overview of what has been my career. I don't know. So, sorry. Can you see my screen now?
Yes. Just have to put it in full view, maybe.
Oh, yeah.
It's
okay,
good.
Thank you. So I will show you a little bit of everything that I have done in the past year about radical chemistry, working with photocatalysis and electrochemistry. And for this, well, I would like to start talking a little bit about the ketones. So ketones are, as you all might know, are prevalent moieties present in many organic molecules that are part of perfumes, natural products. Of course, they are very stable and they present a very versatile reactivity. And all of these make them essential building blocks in organic synthesis, because as you all know, they are precursors of a lot of functionalities such as alcohols, amines, double bonds, triathols, cyanidrines, etc. Therefore, it's easy to understand why we are still looking for different methodologies that allow us to introduce such moiety in more complex structures. Taking this into account, I would like to come back a little bit in the history and talk about a work developed by Paul José de Mayo in 1962 that described that 1,3-diketones reacted with double bonds under UV-light irradiation to afford 1,5-diketone. So basically, he realized that under UV light irradiation, it is possible to form. How did this work? So upon UV light irradiation, the direct excitation of this 1,3-diketone take place, forming this singlet excited state, and then undergoes intersystem crossing to form this triplet excited state. And from here, the diketone undergoes a 2+2 cycloaddition reaction to form this cyclobutanol intermediate that, upon retroaldol condensation, affords the 1,5-diketone. As I mentioned before, this methodology was very useful, and indeed, it was largely employed in the mesembrine or the antitumor agent Taxol. However, this methodology also had one limitation, and it was the selectivity in the excitation process, because the UV light is not very selective, because many functional groups came with the hypothesis that photocatalysis might solve this problematic, because the photocatalyst might be able to selectively excite only one of the two partners, and this using visible light. So our idea was using the photocatalyst excited state and then undergoes the 2+2 cycloaddition reaction to form this cyclobutanol. From here, a retroaldol condensation will afford the 1,3-diketone as in the classical De Mayo reaction. So with this in mind, we proceed to study the reaction with different photocatalysts, but only the ones with a triplet energy above 60 kilocalories per mole afforded some conversion. And this data was very significant. After some optimization process, we were happy to isolate the product in an almost quantitative manner under blue LED irradiation. We were very happy with this result, but then we wanted to know more about our electron withdrawing substituents in different positions of the aromatic ring, and we obtained in every case very good results. We also performed the reaction with beta substituted double bonds, such as obtaining the final product in a complete with the retention of the configuration of the double bond, meaning that if you start from the E double bond, you get the anti-product halogenolate, and we can also get access to quaternary center starting from the alpha-methyl styrene. However, we had a strong limitation here with the alkyl substituted double bond. We always require the presence of at least one aromatic substituent in the double bond. We then proceed to study the scope of the diketone, and we were happy to see that the electronic nature of the substituent does not have a significant effect in the reactivity, so the reaction were fine with electron donating or electron withdrawing substituents. We can also perform the reaction with alkyl substituted diketone unless this alkyl group is very bulky, such as in the case of the terbutyl, or when we place a substituent in the methylenic position that also has a second electron withdrawing group. And therefore, we perform the reaction with other electron withdrawing groups, and we were happy to see that beta-keto ester with a sulfone or a nitro, the reaction did not work. Finally, thinking about the classical De Mayo reaction, a very common approach of this transformation was the obtention of larger ring systems. We wanted to know whether the photocatalytic version could be also applied to isolate the 7-member ring with a very good yield in both cases. At this point, we wonder, okay, this reaction is ketone in most of the cases, and we wonder whether we could expand the methodology to other kind of functionality. And thinking about functional group with similar electronic properties, we came around with the AZA-AREN derivative. If we take a look at the libraries of bioactive compounds, we will find many of them that present an AZA-AREN moiety in their structure, such as this Thieme-Pipra and Papa principle. If we start with an AZA-AREN derivative and functionalize it with a second electron withdrawing group in the beta position, we can have similar behavior than the enol that we used before. So using the appropriate photocatalyst, we could excite it. This will undergo the 2+2 cycloaddition, forming this cyclobutyl, and upon ring opening and rearomatization, will afford the final product in which we have been able to insert this double bond in this carbon-carbon bond. And indeed, we also thought that this methodology will be this AZA-AREN moiety in very mild conditions in any structure of double bond. So with this in case, and we observe the formation of a very promising 38% of the final product. At this point, Noelia Salaverry joined the project, and Together, we optimized the reaction, and we observed that we could prepare quantitatively this compound using THF as solvent and DBU as the base of the reaction. Under these conditions, the reaction performed well with quinolines bearing either electron donating or electron withdrawing substituents. In this case, it changed this ester group by an amide, a nitrile, a sulfone, or even a second ketone. And this example is very, very interesting because we have been able to functionalize preferentially these carbon-carbon bonds against this carbon-CO bond. An isoquinoline, a quinoxaline, or a pyrazine with very good results in every case. Next, we needed also to see whether the reaction presented the same behavior in the site of the double bond as in the previous case. And again, also perform the reaction with heteroarine substituents, obtaining in the case of the thiophene a very good yield, and in the case of the pyridine, the reaction performed well, but the problem was that here we had a competition reaction between the De Mayo and the Michael addition product. From the alpha-methylstyrene or the 2,3-butadiene, and the process is present the same stereoselectivity starting from the beta substituted styrene. But again, as in the previous case, we have a limitation with preparation or for the expansion of libraries of bioactive compounds. Therefore, we decide to apply it for the functionalization of natural products, such as the estrone, the tyrosine, or the tocopherol. We took them, we functionalized the quinoline moiety in all of them with very high yields. At this point, we decided to examine the mechanism of the reaction. The first step will be the excitation of the catalyst. But here, we have two possible photosensitization steps to take place. It's necessary that the photosensitizer present a triplet energy higher than the triplet energy. For the styrene, it was described a triplet energy of 60 kilocalories per mole, but for the pseudoenamine, there was no triplet energy described. So we decided to perform calculation to get the triplet energy of the pseudoenamine, and we calculated not only the enamine, but also the styrene, so we can get an idea of the deviation of the value afforded by the theoretical calculation in comparison to the real value. And as you can see, it's around 5 kilocalories per mole. Anyway, what is important to say is that there is both components of the reaction. And indeed, when we perform fluorescent quenching studies, what we observed was that allowed us to elucidate which of these pathways is the real one. Then we stopped for a second and we came back a little bit over the optimization table, and we realized that with the iridium PPY, we could isolate the final product in 80% yield. But if we take a look at the triplet energy, we observe that it has 55 kilocalories per mole, meaning that in principle it's not able to photosensitize the styrene, but it should present a really strong interaction. And this result allowed us to determine that after the excitation of the catalyst, an energy transfer between the excited catalyst and the pseudoenamine takes place, forming this triplet that then undergoes that the De Mayo reaction is a method that allows the preparation of 1,5-deoxygenated compound in a very easy manner. But what happened with 1,4-deoxygenated scaffolds? This structure is present in many natural products of interesting biological properties. And if we take a look, we find many structures that contain this 1,4-deoxygenate 4-diol derivative that is the precursor for many other interesting structures. Therefore, it looks like it's interesting to count with methods that will allow us to prepare this kind of structures. However, if one take a look at the retrosynthetic analysis of this structure, one immediately sees that from the starting material, there is at least one that must present unpolluting reactivity. Otherwise, it's not possible to connect these two fragments. The functionality or the reactivity of many functional groups has been the opposite as is traditionally in ionic chemistry to prepare this 1,4-deoxygenated scaffold. One example is this one synthesis of 1,4-diketones through enolate heterocoupling. In this reaction, to one of the ketones react with a base and with an oxidant, and the enolate is oxidized, forming a radical in this position that is consecutively trapped by a second enolate, forming in this way or commonly known activation mode is the somocatalysis described by Macmillan. In this reaction, Macmillan and the resulting radical can be consecutively trapped by this DMS-protected enolate, yielding this 1,4-diketone alcohol derivative. In all these methodologies, the commonest they have in common that they start from ketones bearing an appropriate leaving group in the alpha position that is reducted by a photocatalyst, forming a radical here that then reacts with the double bond intermediate. And then this carbocation is trapped by an alcohol or water present in the media, affording the 1,4-keto-alcohol. An electrochemical method to prepare this kind of scaffolds. And why using electrochemistry? Electrochemistry allows to reach higher redox potentials. It allows the performation of several consecutive oxidative or reductive electron transfer in one reaction pathway, and of course, it uses electrons as simple reagent. That in a first step, this ketone might be oxidized in the anode, generating this radical, that then react with this double bond, generating this new radical intermediate, and that is similar or equivalent to the one that we have seen in the photocatalytic reaction, that then will be trapped by an alcohol or water present in the media. So with this idea in mind, Ian McLean, Laura Blanco, and Elena Echavarri started to work on the reaction between 1,3-diketone and double bonds under electrochemical conditions. But to our surprise, instead of obtaining these 1,4-keto alcohols, we obtained the 1,4-keto benzoate, in which through the nucleophilic attack of the alcohol to one of the ketone residues, forming an hemiketal intermediate that evolved with ketones bearing either electron withdrawing or electron donating substituents. As you can see, the electronic nature of an electron donating and a neutral, or an electron donating and an electron withdrawing substituent, we isolate. Then we proceed to study the effect of different substituents with different electronic properties. But as you can see, either electron donating or electron withdrawing substituents in the desubstituted or monosubstituted this molecule to its reaction with phenyl magnesium bromide. And we were very surprised to see that not only the ketone is functionalized, affording the tertiary alcohol, but also the benzoate is activated and is eliminated, affording the double bond, being possible to achieve beta-gamma unsaturated alcohols. However, if we conform the molecule to a simple Lewis acid, we don't touch the ketone, and what we get is the beta-gamma unsaturated ketone that are very difficult to prepare through direct methodologies or direct synthesis using other methodologies. Then we observe the molecule and we say, okay, we have the 1,4 oxygenated compounds, but can we get the diols, or can we get two alcohols that can lately functionalize sodium borohydride? We are able to reduce exclusively the ketone, so we have a nucleophile, alcohol that is a nucleophile in this position, and our diol completely free. And moreover, we could demonstrate that this methodology allowed us the direct CH functionalization of this phenyl cyclohexene. If we submit this molecule to the electrochemical condition, we can functionalize it, and in the presence of this Lewis acid, we can recover the double bond, and what we have done is basically...
I don't understand. Is the selectivity of the reaction site controlled by stereochemistry, by frontier orbital? Yeah, I guess it's frontier orbital, so, all right. Okay. Does the
a very strong group with a very strong electron withdrawing character, but still, I think you will always have mixtures between the two different enols, and in the end, you will always have mixtures of radioisomers at the end. I don't. Indeed, we tried this once, but we couldn't control. That's why we didn't go further with these unsymmetric 1,3-diketones, because from this alcohol, then it looks obvious, or in principle, no, it seems that it should be like this, but it's not. So we're still working on this, because we don't to get to understand why this is happening.
Yeah. Okay. Thanks. I'm just trying to look at some questions. Maybe then it will be the last one, I guess. Yeah. How would you extend this chemistry? At least the De Mayo probably to have an enantioselective version.
Performed an anti-selective version. I mean, you have different options. It's not true. So there are different possibilities. If you start from a chiral compound through the formation of a cyclobutane, that is quite restricted. So in principle, if you start from a chiral compound, this chirality is transmitted. And indeed, this was done before with the classical De Mayo reaction. But with the photocatalytic one, there is nowadays only one example of, as far as I know, of an antioselective catalytic De Mayo reaction with zirconium and some phosphoric ligands. Very specific. So the ligands are very complicated, difficult to prepare, and it's a very specific example, but it works very well. And they only study the classical De Mayo reaction between the 1,3-diketone and styrene.
Yeah, thank you very much for this very nice presentation. I will give the word to Cyril.
And I would like to thank you also for giving me the opportunity to be here today and for organizing all of this.
Yeah. We have also to thank you for that. We have to thank also Thieme for giving us.
Congratulations, Léa, for your nice lecture. Thank you to everybody also for us of seminars. So now it's a pleasure to welcome and to present the second speaker. Is Luca Dell'Amico. So Luca was born in Carrara in Tuscany, in Italy. So it's a really nice place. He completed his Master of Science in Medicinal Chemistry at the Parma University. And then he started his PhD on stereoselective synthesis of biologically active compound under supervision of Franca Zardini. Catalysis of Aarhus University in Denmark in the group of Carl Jorgensen. Then Luca moved and during this time he worked on the development of novel stereoselective light-driven process. So he became an associate professor in organic chemistry at the same institution. So he was awarded an ERC starting grant to investigate a new mechanistic pathway on organophotoredox catalysis. So today is going to talk about from energy transfer to electron transfer process. So Luca, great pleasure to thank you.
Yeah. Thanks for the introduction. I hope you see my slides. 1 second. Okay. Yeah, today I will focus my talk on the design of new photocatalysts. So I will start with a couple of examples from energy transfer to electron transfer catalysis. So first of all, I want to mention that in the research group, we have 2 different research blocks or targets. And in the second research lines that which I will discuss today, we like to develop new photocatalytic system to open new avenues in synthetic catalysis. So basically today I will focus on other reports on the same topics that we reported some time ago. Okay, let me see. So this is the summary, the graphical summary of what we developed over the last few years about good and balanced redox potentials. And at that time, the well-known 4CZIPN was still not the well-established photocatalyst in the field. And we developed a highly reducing phenolic-based photocatalyst in collaboration with Professor Filippini at the University of Trieste, and actually we did so by studying the reaction mechanism, transforming a stoichiometric reagent into more on this right part of the screen that you can see. So about the development of these two classes of molecule, one to be used in energy transfer processes and the other one to be used an electron transfer molecule. So we started the projects because we were actually is good, is stable. We can have different exit vectors, and unfortunately, and this is because, of course, not because it's not a good bioisoster or it's not a good unit in the pharmaceutical from the pharmaceutical point of view, but because as synthetic chemists we are not very good in building azethidines. It's not very simple, and indeed we still rely on old-fashioned chemistry. So if we think about the construction of an azethidines, so we can envision an intramolecular displacement. We can also start from the corresponding lactam, and then it has to be tailored to perform this type of process and involve, in some cases, harsh reaction condition and tedious multi-step form 2+2 heterocycle addition reaction, so a NASA-Paterno-Bucchi process, for example. And I have to cite Corinna Schindler. There are some limitations because you have to somehow block the configuration of the imine. Otherwise, upon light excitation, it will start to isomerize. So you can somehow have problem of reduced reactivity, and also you can have problem of regio and stereoselectivity in this type of processes. Another approach is to use as a basically strain release. Of course, you can imagine this nitrogen-carbon bond wants to break up to free the stereo control of the reaction, because we have the nitrogen which is nucleophilic. So we can use a reagent where this dark blue circle is an electrophile, and then we can have an incoming nucleophile, which can functionalize the C3 position of the azeth. And I have to mention also in this field, Varinder Agarwal, among the others, did reported a lot of nice signal, and this can perhaps open this as a bicyclic scaffold. So basically, this was the idea. So to use a cleave, homolytically cleave these bonds here to generate two different radicals. Now, the first radical can add to the ABB, generating this more stable tertiary radical that can undergo radical combination with the second one with installation of Ricardo, which is the postdoc that is working with me, and was his own idea to develop this type of chemistry, investigated a lot of different classes of reagent, and he found this sulfoxamine to be the ideal candidate to perform this chemistry. So it tends to break up. So we can generate this sulfur center radical and the imine radical. Now we can have the first addition of the sulfur center radical to the ABB. We will generate this stable tertiary benzylic radical, will undergo radical combination, installing the nitrogen at the C3 triplet sensitizer. With the classical ones, such as thioxantone or these BN derivatives. So basically, we always had the problem of isolating the desired product with this dimer. Consider, sorry, it's been stuck. Okay, so if you consider the reaction manifold, this radical here has to stay there and wait until you can imagine that if you generate too much of this imine radical will tend to dimerize. So they will start to react together to enter in the reaction. So the delta ST is the energy difference between the singlet state and the triplet state. This gap is very short. Basically, the photocatalyst is going from the singlet state to the triplet state, and from the triplet state back to the singlet state. So you have this process where the singlet and the triplet are going back and forward. So basically, having a very short gap in the reaction. So basically, you have a weaker, a worse somehow triplet sensitizer. But in our case, was key because then we can tune very well the amount of the formation of the imine radical. So we can have less imine radical in the reaction, and this will result in a better selectivity. And in this case, we were happy to have about 90% selectivity for the desired compound. We then perform some mechanistic investigation. So this is the mechanism as I showed you before. So we are exciting the photocatalyst. the sensitizer. The sensitizer is sulfur bond, the first addition, and then radical 11 can add to the incoming tertiary benzylic radical to generate compound 3. So of course, by Stern-Vormer analysis, you can nicely see that the photosensitizer excited state is quenched by 2. And then we performed some laser flash photolysis experiment to characterize mainly compound 12, which was never reported before. And we corroborate this. And then we assign to this band around 490 nanometers the absorption porphyrin of 12. This is in agreement with this last experiment where the absorption at 400 nanometer is in compound 12 is coming from the reaction between 10 and 1, coming from an increasing amount of the ABB. We also perform EPR experiment, in this case with a spin trap, so you can shine light on 2, and then you will start. Then when you add the ABB, you see a completely different spectrum, so it's this red one here, which correspond to the trapping of the radical 12, so of this key intermediate in the reaction. And we can simulate this, and you can see this is matching quite well with the experiment. Okay, then we perform the scope of the reaction. I don't want to annoy you too much on this. You can check on the paper. The reaction is very general. As I told you before, you can really rational design your synthesis, and you can have also complex starting material embedding biological active compounds. Of course, now once we prove that you can generate this tertiary benzylic radical, so we were happy to play with it. So we can, of course, start trying to trap with a different somophile. So you can add an H dot at the C3, or if you use this SCF3 the malemide, you can install the SCF3 functionalities. We did this for a variety of different compounds. Okay, then now with the scaffold in hand, you can also think to the protection, so you can free the primary amine. You can, and Ricardo was very into developing this oxidative ruthenium catalyzed dearomative process to install these exotic spirocyclic compounds, actually in quite a good yield. Catalyst. So you can see here that the molecule is, the strain molecule is released by the action of light and the presence of our photocatalyst. And here the people that were involved, I told you, was Ricardo, which is Mexican postdoc, then Lorenzo and Stefano, which are PhD, and the example is about electron transfer. So in this case, we actually wanted to solve a gap also, which is in the literature. And basically, when we want to perform a reduction and we want to use an organic photocatalyst, particular for the synthesis of polymer or for the activation of inner carbon halogen bonds, we rely on this type of scaffold, well, in replacing iridium. So, but why we want to replace iridium? So this is well discussed in the literature. We don't want often to use iridium, apart from the price that may be varying depending on the financial situation, but by photoreductions, then the photocatalyst will stick into your polymer. And you don't really want to have iridium if your polymer is used for any biological application or med chem application and so on. So you may want to have a tiny amount of an organic molecules, which is of course safer, and avoid the presence of. Basically, they are characterized by an electron-rich core where the HOMO is located, and on the nitrogen we have this other aryl way that upon excitation, the excited state, in the excited state, one electron will jump from the HOMO to the LUMO, generating a charge transfer excited state when we have basically a radical cation on the core and a radical anion on the external ring. So in this case, is well known that the photocatalyst excited state is long-living enough to better perform the chemistry. So what we wanted to do in the group, it was actually to free one of these two nitrogens, to have the free NH, to engage the NH in the HOMO and the LUMO. So we designed the system to have the HOMO on the core, as in the previous reports, and we decided to place this external aryl group at position 9 or 12 to accommodate the LUMO. We were initially guided by simple DFT calculations, so you can see here some example. So indeed, if you look at the DFT, the HOMO is located on the core and the LUMO is located on the external aryl ring. So for both classes of compounds, the simplest one or the one with electron donating groups, this is true. So HOMO on the core and the LUMO is in the external ring. And indeed, we can prove that with the cyano impara here. So basically it's the same photocatalyst at the same concentration, and we are looking at the emission in different solvents. So basically one electron is moving to from the nitrogen to the aryl ring. So, and basically we free the radical cation on the nitrogen and the radical anion on the aryl group. So we have a Church transfer state which has a cationic character. So which has what is called Church transfer excited state. So and have a partial cation state. That's why we observe different colors, because different solvents are stabilizing in a different way the Church transfer excited state. So this was kind of the proof that we have indeed a Church transfer excited state. These are the summary of the photophysical properties of the molecule. We also prepare this more extended conjugated system to move the absorption more to the visible. I will not go in details, but I want to point out that all the molecules are varying. So we first benchmark this class of compound within known transformation that were performed by. So we screened the molecule and we found the best one to be this compound 5A, which is this molecule here, 5, with the hydrogen at the para position of the external aryl ring. So we keep moving with this molecule for further studying. And what we actually wanted to do, as I told you at the beginning, it was to engage this kind of new photocatalyst in hydrogen bonding complex to open to new type of reactivity. So we screen a different complex, this hydrogen bonding complex here. Now we can shine light and excite this complex. So usually we'll have a radical anion with the formation of the chlorine minus and the radical 9. Now you can do a lot of chemistry with radical 9. In our case, we wanted that just to prove the mechanism, so we can furnish an H dot to install the hydrogen here at the para position. And to do so, we furnish, you will have the formation of the corresponding radical cation of the nitrogen, right? Because if you move one electron to the nitrogen to 10, you will free the radical cation. But now we have the hydrogen bonding. So basically, what is happening is a proton-coupled electron which is transferred to 10, while the other electrons that is involved in this nitrogen-hydrogen bond stays on the nitrogen. So you can see you do not form the radical cation, but you form 14, so the nitrogen center radical. Why this is important? You can have kinetics and thermodynamic benefits. So you skip this very highly energetic intermediate, you radically go to this radical 14, and of course, you generate the conjugated acid of the base. And now to restore the photocatalyst, you need to do an hydrogen atom transfer. You can use the same gamma term bonding complex by looking at the NMR. So here is lying the NH, unfortunately behind this aromatic signal, but you can clearly see that this is moving at the increasing amount of the hydrogen bond acceptor. And also you can see by cyclic voltammetry, the black line is the photocatalyst is becoming easier to oxidize. So basically, it will be a stronger reducing agent in the excited state of about alpha volts. So this is very important observation. You can also DFT the complex with our proposal. So as we are synthetic chemists, we wanted to apply this and to show that we can have some benefits. We can have ammonium and other are shown in the groups. I don't want to show you. And we wanted to show the benefits of using a proton-coupled electron transfer manifold. So to better compare, we prepared the same photocatalyst in a methylated version. And here, of course, this cannot engage in a hydrogen bonding complex, basically. So we do not have the hydrogen, right? So we can only have the electron transfer manifold. But you can see at different times with different one working. And I generally like to point out of this example of this compound 24 is basically the same of the ground state, of the redox potential of the ground state compound. So this, it means that thermodynamically, you do not have, but if you go through the PCT manifold by proton-coupled electron transfer, I show you before, you basically extend of about alpha volt the redox border of the photocatalyst. So now the chemistry can, of course, it's difficult, it's challenging because this molecule doesn't want, we start to observe some reactivity. So basically we are expanding the redox properties, the redox profile of a photocatalytic. Catalyst replacing iridium, in some cases working much better, not only for polymers, this as we also show in the paper, and functionalize. Now we have different generations in the lab. And I have to thank my friend David Leboeuf, which reported for the first time this molecule in this work, and then we start our collaboration together. And also is a nice point that we can form catalytic ADA complexes, and this we have shown this in care too much about the redox potential. So the electron transfer will happen independently by this, because you have basically a same. Okay, now before closing, just a few slides about project that we recently submit, and you can find it in a preprint version. So we are actually, as I showed you before, very interested in performing and expand different molecules. For example, I show you the activation of alkyl halide, aryl halide, but we can also activate ketones, CO2, for example. So you can oxidize alcohols, amine, carbamate, olefins, aryl groups, and so on. So in this case, the major part to do an oxidation, you are more here. And you use this type of molecules. So if you don't want to use, of course, transition metal complexes, so you can rely on acridiniums to perform an oxidation, or you can use phenothiazine or acridins, as I showed you before, to perform a reduction. So I got very obsessed in trying to expand and to merge both manifolds. So can we do at the same time two compounds? Can we activate compound 1, breaking these carbon-chlorine bonds, and at the same time oxidize this benzyl Thieme? Very huge spectrum to access. We have to go from basically -3 to 1, then to screen photocatalysts. But of course, the classic photocatalysts, they do not reach the potential to activate these substrates. So we always met with failure using EPM derivatives, but we also try iridium and ruthenium. These are not working. You can try to use very electron-rich systems, but this we can only activate, of course, the starting 2 by oxidation. So in our naive point of view, we start to mix the photocatalysts. And I can tell molecules, we observe some reactivity. So we start to observe compound 3 in around 10% yield. And we got interested and we thought, okay, let's try only the acridinium 7 in the reaction. And actually at that time, we got 33% yield. So it makes sense that the acridinium is activating 2 by oxidizing the process. So basically what we observed was the dimer of 2, so the dimer 10, which is coming from 2 oxidized molecule, and upon, of course, silicon excision and formation of the radical. We can observe the formation of the bond, as was reported by Fukuzumi and Naisiewicz. But we were very surprised to see that we were also activated 1, because we observed the cleavage of the carbon-chlorine bonds with the formation of 9 and the dimerization of 1. But the most interesting on the acridinium compound, but we only observed the formation of this dimer, of this acridine dimer that we call Phoenix 1. And you basically have great reactivity, and you can see here, you can access really high and broad redox margins behind 5 electron volts with the same molecule. So you can activate, for example, Wainwright amides, different amides. You can activate ketones, change the nature of this benzyl TMS. You can have heterocyclic system. You can have thiols, olefin, and so on. Laser flash photolysis experiment, and we also perform EPR in collaboration with Marco Bortolus at the University of Padua. So basically, if you shine light on this dimer, this was known actually in an old paper of the cell electron will reduce 7, generating another radical 13 that will dimerize with the regeneration of the starting compound. By laser flash, we did observe the formation of the acridinium, of the radical 13, and of the presence of the free radical in solution. So now if we start to reducing, so it can activate this carbon-chlorine bond with the generation of 12. So the reaction now is becoming irreversible. TMS to perform the oxidation. And now 12 and 14 can couple together in a radical combination to generate the product. And machinery is that radical 13 likes to dimerize to regenerate the photocatalyst, the starting material. That's why we call Phoenix, because initially the photocatalyst with this, like this mythological bird. So in this manifold, we can access a very broad range. Show you is a very reducing species. how can we have selectivity in such a mechanism, in such a catalytic manifold when 13, which is a key radical which is coming from the catalyst, this can be trapped, as I showed you before, by the benzylic radical or also by the radical 12. But the nice point is that in these cases, if you shine light, the reaction is reversible. So the reaction of 11 upon light excitation will release the radical 14, and excitation of this compound 15 will release radical 12. But what is irreversible is the reaction within the formation of the product, apart from being the more stable compound. Even if this absorbing under visible A will not break this carbon-carbon bond. So this is acting as a sink to release radical close. So we were able, in this case, to merge the two opposite quenching manifolds. So within this type. Okay, just a couple of words. Tell you where is Padua. Is in the northeast of Italy, very close to Venice. So it's a beautiful Renaissance city. So if you are passing by Venice, celebrated actually now 3 years ago our 800th anniversaries. And of course, I have to thank all the people at paper. It was Christian, Tommaso Bortolato, which is not in this picture, and Gianluca, which is PhD in the group, and in the last project, Georgia, Alessia, and Christian are involved. And of course, I want to thank all the groups this event.
Okay, so thank you very much, Luca, for this wonderful talk. A lot of new things and very interesting also what you present at the end. The first topic, you mentioned mechanism where in fact at the beginning, so if you can see slide 5, for example, where there's the sulfonyl group that you generate, so the radical and the benzylic radical by addition on your compound, your amino compound, and you form so this benzylic radical. So this is, yes, slide 5.
Okay, maybe I can do like this, I think.
Yeah.
Yeah, it's better if I keep it like this, if you can see.
No problem. Okay. After, just 5, we can say 6, yes, maybe. This one. No, it's just before, I don't know, intermediate 12. And yeah. You propose so coupling reactions between this a lot of intermediates, but particularly, in fact, this, I say this tape. Are you sure about this one? Is it possible, in fact, for example, to imagine a chain mechanism where there's quite low, in fact, for an activated chloride? So I was thinking, could you clarify how you determine it by CV calculation?
Yeah, this by CV in isopropanol, which is the solvent of the reaction. So you can, but also in acetonitrile is not so far. And actually, we also got some similar comments from the reviewers, but this is the experimental data. So if you have the ketone, yes, the ketone is around minus 1.6, minus 1.7, but the esters is all the value of this compound with methoxy, ethoxy, and so on is in the range of minus 2.7, minus 2.9, and then when you have the when-ribamine is going behind the redox border, so you cannot see the reduction peak. The ester, no, these are easier to reduce. Yeah.
Okay. So that's Babing that asks, is the Phoenix one, your intermediate, we have your slide, is isolable? Could you isolate this one?
Yeah. It's a stable molecule, yeah. So you can basically, so it was one of the byproduct of, so if you take the reaction with acridinium 7, you will only get 1. So we were able to isolate at the end of the reaction only 1. And also I can add, if you take 11, at the end of the reaction, you will see 1. So you will see Phoenix, because basically you excite, you break these carbon-carbon bonds, and then this radical really like to dimerize. If you look at the kinetics that we measure with the by laser flash is in the diffusional limits. So you can isolate compound the compound, and also we prepare different variants with different groups, extended versions, and so on.
Okay. And there's the intermediate 11 is intermediate 11 is forming. So I don't know intermediate 11. What is it? Something.
12. This one. Yeah.
Yes.
This we observe the formation of this intermediate in the reaction because of course you can imagine that 13 and 14 they can using species in the reaction as the same phenix, so both can reduce the starting material, but at the end of the catalytic manifold, as I told you, so we have the sink with the formation of the product 3, and then you free a large amount of the radical 13, which will likely recombine to regenerate phenix. But the role of 11 in the reaction is proved, we observe, and it can also catalyze the reaction.
Yes, and there's a question of Fan that ask, could you give more comments about the stability of the radicals to generate the radical and the radical cation on the nitrogen center systems? What is the stability of this system, and particularly in this case, the charge transfer? Ask about the
you mean here or so?
So I imagine yes. This is yes, exactly. Exactly.
So how stable is this nitrogen center radical? Well, difficult to tell because, of course, let me think about. Yeah, we observe this by EPR. So we perform radical trapping, and you can trap this nitrogen center radical, and it's also reported that this, if you generate this by electrochemistry, this will how can I say, interact with the surface, so can actually poison the electron somehow, but is a proof of the generation of this nitrogen center radical. Apart from this, I don't have much more insight. So the lifetime should be around in the nanosecond scales, but I cannot be more.
Ask, do you check the triplet energy of your substrate and the phenix one? Is it possible to have a merge of photosensitization and electron transfer in your mechanism?
Basically, upon excitation by laser flash, we neither observe the singlet because this disruption is so fast. So we immediately see, of course, have time to see a triplet state because we can go from 1 nanosecond to hundreds, but we never observe the formation of the triplet state because what we are doing now a collaboration to do femtoseconds laser flash to see if we can observe the singlet state and the generation of the radical. But in this paper, this whole paper is known, so they also check by laser flash, and is known that it's extremely fast, so below nanoseconds. So you do not access the triplet state in this case.
Again for this stimulating lecture. Thank you very much, Luca.
Yeah. So thank you, Cyril. So last speaker, last but not least, but probably due also to a little bit of jet lag, we have now David Najib from Ohio State University. So David grew up in Philadelphia, did chemistry studies at Boston College as an undergraduate, and then got his first research experience with Prof. Scott Miller, working on peptides, and then he did his PhD in Princeton with Professor Macmillan. He got his PhD in 2011. And then he went to the West Coast in Berkeley, working with Dean Toast, where now he's full professor and also distinguished professor. So he had a very fruitful research career. I mean, working on a lot of interesting reactive intermediates, radical and carbenes, and he's going to present us this, focusing on the radical polarity, because he had a very interesting recent paper in JACS describing this concept, which is very key concept in radical chemistry, and actually, I would say in organic chemistry in general. So thank you, David. And you can start.
Thank you, Louis, so much for a very kind introduction, and obviously for the opportunity to come to Europe, even if just for a few hours this morning. I appreciate it. Really enjoyed the symposium, going so far. Congratulations to both Vera and Luca on really excellent work. So my lab has been interested over the last 10 years or so in different types of remote CH functionalizations by radicals. I just show you here 3 of the mechanisms: the delta CH functionalization, the gamma, and the beta. And you see many of the synthetic transformations we've developed from there. And in a parallel program, we've also been interested in the polarity of radicals, and specifically the reversibility of polarities. So for example, taking a carbonyl group, which is inherently an electrophile, converting it to a nucleophilic keto radical, as well as a carbene and even a dinucleophile in this dimetal species. But today I decided maybe it would make most sense for this venue to focus on our recent radical polarity studies, and then just show you a few examples of how they have informed our thinking of the remote CH functionalizations. So by way of just a 1-slide introduction, I thought I could put together here some key reviews at the bottom in case you're not familiar with this area. I think these are very good introductions, both recent reviews and older ones. Or I could just give you the sort of simplest introduction to how we think about the polarity of radicals. So today you saw these 2 starting materials already beautifully used. I'll just talk about how we think about this alkyl halide. You know, when we're thinking about organic chemistry without radicals, we tend to think about bromide anion leaving, a cation which is inherently electrophilic, but a stabilized cation here thanks to hyperconjugation of these alkyl groups. Think of this as a nucleophilic radical, or the polarity reverse of the electrophile that you get from the same starting material. We also saw earlier today this more acidic starting material where the 2 esters are going to acidify the H, so we could deprotonate it easily to make a nucleophile, in this case of an anion, of course a stabilized anion with these withdrawing groups stabilizing the negative charge. Or again, if I just simply homolize the bond, a formal hydrogen atom transfer, now the open shell radical intermediate has an electrophile, and then as well as a reversal in polarity between the 2 electron and the 1 electron system. So that's sort of an outline for what has always intrigued me about the polarity of radicals and how you can access different reactivity. And in preparing for this talk, I was sort of thinking, how long has it been that I've been thinking about this? And then, of course, you know, it dawned on me that if I could open up my PhD thesis, my entire PhD was obsessed with this one radical right here, carbon radical with 3 fluorines inductively pulling away on it, making it an electrophilic radical. Admittedly, I spent the majority of my time in my PhD thinking about starting materials that could access this radical via single electron reduction. The limitation there, of course, is if you have to overcome a very negative reduction potential, an electrophilic radical is happy to take another electron. So you see a small gap here between -1.5 and -1.8. You get to the anion, and now you no longer have electrophilic reactivity. Electrophilic radical with pi nucleophiles. And then what I wanted to show you was sort of the thinking as how my PhD progressed. So originally we started with what Herbert Meyer in his nucleophilicity index here describes. An ene is 5 orders of magnitude more nucleophilic than the silyl ketene acetal. And indeed, after publishing our first trapping of a CF3 radical with an enamine, we then moved on to silyl ketene acetals, and then enol silanes. And finally, for the last project, you could see we went to very, very weak nucleophiles, really as a testament of how electrophilic the CF3 radical is, the work of Herbert Meyer in cataloging and categorizing these polarities. All right, so then I started my independent career, and I knew that a CF3 radical was an electrophile. I knew that it reacted well with nucleophiles, but not with electrophiles like these pyridiniums, which are very common in medicine structures. And so Jeremy and Quentin, 2 of my early students, said, aha, we have an idea. If these this radical electrophile and this electrophile are polarity mismatched, we could do a 3-component reaction with these electrophilic radicals first combining with a nucleophile in the same flask as the electrophile, because these are polarity matched. And now the new nucleophilic radical, by virtue of moving the withdrawing group further away, should now do a simple Minichi reaction into this pyridinium. Philic radicals are matched with nucleophiles. And so over the years, we've sort of been thinking about how to how to sort of categorize this knowledge and put it with the other things, the other resources I say that are invaluable in our lab. These are the sort of posters that we have hanging up everywhere. We're looking often at these pKa studies, as well as these Nicevich redox potential studies. So we often look at Herbert Meyer's nucleophilicity indices of the 2-pi, the 2-electron systems. And then last but certainly not least, we've always loved this work of de Proft, categorizing the polarity of radicals. You see here in this one paper that I've highlighted, just a couple, but really, really instrumental in governing our thinking. And so I would say a little over 5 years ago, Jake and Andrew sat together and said, wouldn't it be nice if we could expand time? And we basically said, our version of a review will be to take every single radical we see and measure its polarity using the de Proft calculation. So here's our database that we recently published. If you're interested in it, just Google the word radical polarity, and I believe it'll be one of the top hits. So you'll see here the nucleophilic series in blue on the left, electrophilic series on the right in red. Workflow here, we use the Ohio supercomputer, optimize the geometry of each radical, and then if a radical is nucleophilic, it's easy to oxidize it, so we did that oxidation. If it's electrophilic, it wants to take another electron, so we did a reduction. Then we took the ionization here. For those of you interested in this polarity term or electrophilicity term, I compare it to the term power, which is voltage square over resistance. And so what Parr found was electronegativity squared over hardness. And again, de Proft extended it here to a computational chemist, although my students have proven to be excellent ones. So with that regard, what we were hoping to do is take this computational database and develop an experimental validation. So I just show you here 2 of the many ideas we tried, competitions, but we could never really get a comprehensive set of validation experiments. We did the same thing with electrophilic radicals, performing hydrogen atom transfer with a nucleophilic or a more hydridic CH over an electrophilic. Again, we just couldn't get the sort of broad experimental validation that we were hoping for. That is until we thought about hydrogen atom transfer in the opposite direction. That is, if you take a nucleophilic radical or an electrophilic radical and do hydrogen atom transfer to it, vice versa, BHT would react because it's electrophilic more rapidly with a nucleophilic radical. And you can imagine competitions where the nucleophilic silane should react more rapidly with an electrophilic radical rather than a nucleophilic radical. So here we simply bought or made every carbon iodine bond that we could get our hands on. That was reflected in this database. We shine light and introduce the silane, and lo and behold, so certainly the aryl radicals stand out as being not particularly on the trend, right? These are reactive systems. They all sort of cluster over here. But in blue, I show you some of the most electrophilic radicals up top here reacting rapidly with the nucleophilic silane, as well as the most nuclear. I certainly love the outlier terms. So I highlight here the tert-butyl radical here. If you notice, the calculation didn't take into account any steric component. And so we imagine that explains some of the outlier behavior here as well. But okay, that was our first attempt at an experimental validation. I just map here what I just showed you, a 0.8 correlation between the polarity term and the reactivity term. This, of course, is a kinetic term. We often sort of think of radicals first and foremost in a thermodynamic sense with bond strength. So we wondered, are all the CH bonds that we were making in that series or the CI bonds that we were breaking here, see some negative, but a resource that would be useful. We were very interested in the benzyl radical series that de Proft had developed. So we basically filled in the gap with every single R group at a para position that we wanted. I'll just sort of highlight maybe my interest with, knowing the difference in polarity between a para withdrawing group, a para donating group, and some group in the middle. And then maybe even more interestingly, knowing that these are additive properties. So you could take these benzyl radicals, make them tertiary, secondary, primary, and the series and the relationship we saw up above. So Hammett values up here, the polarity values on the x-axis. We actually found a very nice correlation. So that was interesting, both for the benzyl radical series and then another series I'm not going to show you here, but the phenyl radical series, we did the same sort of para substituent, saw a very nice correlation as well. All right, so I'll just go through two heteroatoms that interest me dearly, the oxygen-centered radical. Here I just wanted to show you the power of resonance. So the lone pair on this oxygen donating in makes many of these keto radicals or keto radical anions much more nucleophilic than the alkyl series on the previous slide. As opposed to when you walk that oxygen out so that it cannot resonate, but simply behaves by induction, you see here a much less nucleophilic or even more nucleophilicity. Another comment I wanted to highlight here in purple, we compared polarity with Hammett. We also did with acidity. So you can see here, I guess Luca was showing some nice reduction potentials here. So you can imagine the easier to reduce or excess radical and so on. And then last but not least, my favorite example to highlight here is this acyl radical. So if you put an open shell right here at the carbonyl carbon, of course, although an aldehyde is electrophilic, that carbon, a radical is nucleophilic, so a polarity reversal. I think this is one of those radicals that the radical experts all know this is a nucleophilic species, and so advantage of using radical intermediates. And then last but not least, my other favorite heteroatom is a nitrogen-centered radical, and maybe another surprise result for some, because I don't think it's articulated very often in literature, but a nitrogen-centered radical is nucleophilic, not as much as a protecting group or an azide. Then you get into the electrophilic series. So some of my favorite nitrogen-centered radicals veer more from the sp3 to the purple series here, just showing the protecting groups as you go from a tosyl to a more withdrawing triflyl to two tosyls or two sulfonyls. You can see the increase in electrophilicity. Why does that matter so much to me? I just wanted to zoom out here. I was sort of working through the functional groups of carbon-centered, really beautiful kinetics work on radicals. So I showed you HAT with a carbon-centered radical. Here it is with oxygen-centered radical, abstracting hydrogen atoms here from a more nucleophilic or a hydridic CH versus a less hydridic one when the gap is very small. So here on the x-axis is a small gap to the left. We saw a small difference as opposed to on the right here, a large gap in the difference of the polarity that you're going to make. Giliaglu, excuse me, Ingold and Sciano, looking at silyl chlorides abstracting CCl bonds. Again, with these benzyl radical series here, you can see the electrophilic radicals reacting much more rapidly than the nucleophilic radicals. And last but not least, we looked at a pi addition series. So just taking these nucleophilic end-centered radicals and adding them into pi bonds with different R groups here on the styrenyl aryl component. And again, just showing the difference here with a more electrophilic trap for the more nucleophilic radical being the most polarity matched. All right, so that is sort of the bulk of the radical polarity concept. What I thought I would do for the remainder of the talk is show you 3 short applications of how this sort of understanding of radical olidine, a 5-membered ring here, by virtue of generating a weak NX, go directly from here to here, all by shining light on this concoction. So we had developed a variant of the Suarez work. I just show you here in our first paper in 2016. But we'd also sort of always appreciated, whereas we could address the limitations of the CH bond, we were sort of often limited by the need for this tosyl protecting group. I mentioned here the acidity is nice, but certainly having to remove it was a limitation that we were often asked about. And you know, we often wondered, why is this nucleophilic radical generating a nucleophilic radical, I should say, doesn't work without acid? Then you put in the radical cation below. These are the polarities that in the radical cation below. These are the cation below. These are the polarities that we calculated for the nitrogen-centered radical. The polarities that we calculated for the nitrogen-centered radical. Here are the polarities we calculated for the nitrogen-centered radical. Here are the polarities we calculated for the carbon-centered radical that you generate. And then we also did bond dissociation radical that you generate. And then we also did bond dissociation energies or bond strength difference to show, I believe there's one more animation here, to show that the radical polarity best predicts the reactivity in this intramolecular HAT more so than the classic bond dissociation energy strength or the thermodynamic side. All right, so that was one application. The second one I wanted to show you is the sort of grown team over the years, thinking about not delta functionalizations, but now beta functionalizations of alcohols. So the idea here is that an alcohol is a common functional group. We thought we might append to the nitrogen-centered radical that I had shown you previously. We could do amination and other versions. So if you're interested in the sort of full story of that development, I'll point you to this 2019 paper. But for now, like the Overman style imidate here, just without an alkene, and then subjecting that to these Suarez modified conditions to give really spot-to-spot beta-CH amination. We could either do an acid workup so that we could do an acid-base extraction, thanks to its robustness, thanks to the sort of radical mediated CH functionalization. So what I wanted to do is update something that we reported in that 2017 paper that never made full sense to us. Specifically, we had just simply calculated the SOMO energies of a trifluoride radical, which we knew to be reactive, as well as a tazimide radical, which we again knew to be mildly reactive, and then these two other groups that we knew not to be reactive, but that flanked the tazyl radical never made sense to us. But it was fine. The imidate radicals that we did, numbers, the true polarity numbers that we've calculated here, you can see here the black ones in the middle are the electrophilic, the ambiphilic triangle delta functionalization and beta functionalization today. I thought I'd give you a little glimpse at some gamma functionalization that we worked on. I simply, James and Taylor put their heads together to come up with a better solution to this chemistry. They were inspired predominantly by this beautiful MHAT work where a metal-centered hydrogen atom transfer can occur, delivering a carbon-centered radical, could do a carbon-to-carbon HAT, and then we could introduce the same trapping mechanisms as above, just at a remote position, triple hat cascade. So did we get it to work? First, let me show you the challenge of sort of what we knew would make. So I'll just give you an example. If it's an alkyl, so we're trying to identify a gray ball here to go in between the carbon-centered radical and the nitrogen in this case. If it's an alkyl, you can see that this is a nucleophilic radical trying to make a nucleophilic radical. That we said was polarity mismatched, was at 1.4 electron volts. And so we said, all right, this alpha carbonyl, or this alpha amide radical would be the one that would work on polarity in that database of over 500. So forgive me that I didn't memorize them, but I know that we calculated it. So here it is, if you can see my cursor here.
Yeah. So the HAT will make a big jump in terms of yield.
That was our expectation. So we've done some kinetics on the trifluoride radical, reacting essentially, in minutes. So in half an hour, we get full conversions here, as opposed to usually 24 hours on our tazyl. So if that's what 2.2 to 2.9 gets you, you see the nozzle idea that you have 2.7 is certainly close to it. I'll say that you can imagine as we sat and built this database up over the years, we've thought a lot about, okay, so, why aren't more people using it? If you think about how we generate these N-centered radicals, often via an NX, we feel like that was the problem. A really acidic NH to combine maybe a photocatalyst and a base, via a pair of mechanisms. But we think that that's the opportunity right here. If you go with these really acidic systems, throw in a little bit of base and oxidant. If you know our work with NFSI, you can see here why we were interested in calculating this Bissell.
Really affect the radical coupling in terms of rates and selectivity. I mean, can you favor hetero versus homo coupling?
Yeah. Admittedly, in my experience, we don't develop a lot of methods that have two radicals trying to combine. I think that's the sort of hardest mechanism of radical combinations. I much more prefer either the homolytic substitutes. Yeah, so admittedly, it's probably 2 rows in the paper. So I'll just encourage the questioner to go look at that. But we put it on the poster down here at the bottom. So here, I think we just put, you can see here, every orange dot represents a silicon atom that we calculated. Yeah. They're kind of all clustered here around 1 electron volt. So they're all pretty nucleophilic. no matter what atoms we put. So you can see here maybe the sort of outlier was when we did Chatty Giglio's large tri-silicon or super silo radical. But you can see here it's not that much more. Showed today was sort of the charged species always are big outliers on the most nucleophilic side or
I think we may have lost Louis' feed.
I see.
Are Karen still available?
Okay.
Hi,
I'm
I'm still here. Hi.
Great.
There was one further question about whether the radical polarity depended on the shape of the radical. So you got CH3 radicals and CF. Fernandez Goodall, the question was concerning electrophilicity for halogens because they deviate substantially from experimental data. Could you?
Nucleophilic carbon radicals from CH bonds.
Okay, thank you. I don't know if Louis or Cyril are still on the call.
I see them.
Yes. Ah, you are back again.
Yeah, I'm back. Yeah, I don't know what happened. Sorry for that. Right, I wanted to thank you, David. I wanted also to thank Lere and Luca. It was a very nice session. Also the discussion were nice and very good attendance. Thanks again to Thieme, and for me, I'm really happy with the turnout of this webinar. So Cyril, probably if you want to say something.
Yes, I want to thank the same. I want to thank all the three speakers that give a very great presentation for the opportunity that they gave us, in fact, to organize this symposium, the second version, maybe the third. We are waiting next time. But I want to say I want to thanks to everybody also that attending to this team webinar. We are quite close than 300 people, so that's a good success. And
thank you.
So much.
I'd also briefly like to say thank you to Louis and to Cyril for chairing today. It's great to have you back on board to do a second version of this. And for a lot to take in, and I'll certainly be going back to watch it again. So I hope that you do too. And hopefully we'll see you at our next web seminar, which is on the 24th of March. Thank you very much, everybody, for listening.
thank you, Karen.
Bye.
Bye-bye.
Thank you.